Okay, guys, welcome to the RI seminar. Today we have Professor Hod Lipson joining us from Cornell University. Hod is an associate professor of mechanical and aerospace engineering and computer and information science. So he is also the director of the Creative Machines Laboratory, which deals in many topics, including evolutionary robotics, artificial life, design automation, rapid prototyping. He just came out with a new book on 3D printing, which is probably pretty good. Works in self-assembly robotics. And I met him for the first time today, but I've actually followed his work for a number of years. He's very prolific, very deep thinker, in fact. He has something like 250 publications and patents, about 200 invited talks, and a huge media presence on almost every media you can think of worldwide. So he gets the word out on what his group is doing. Some background: he received his PhD from the Technion in 1998. Then he did a postdoc at Brandeis, followed by another postdoc at MIT, and came to Cornell in 2001. So please welcome Hod Lipson.
Thank you. Thank you. It's a pleasure to be here today. I wanted to talk a little bit about robots that ask questions, robots that make discoveries, robots that want to be scientists. And sometimes I talk about 3D printing, about manufacturing, about self-assembly, but to speak here, I sent in a couple of abstracts, and this was the one that sort of people wanted to hear about. So I'm going to talk about this idea of robots, what we call the robotic scientist. And it sounds a little bit like we're trying to replace ourselves. We're not. But I'll show you a little bit about how these things work and how we came to do them. Because we actually didn't set out to try to make a robot that does experiments and comes up with hypotheses, but it was sort of a series of serendipity in various ways that made it happen. So I'll tell you the story of actually how it happened, not straight away how it works. So it all started with work we've been doing for a while, trying to make robots that improving robots. And as everybody here knows well, there are lots and lots of robots out there, but by far most of them they work in a very structured environment. They work in factories where everything is in the right place at the right time. They are superhuman in almost any way you want to measure it. They are very fast. They're very resilient. They work 24/7. They're very powerful. They are better than humans in almost any way you want to measure, except their ability to adapt to new situations. So most robots, if a bolt falls off of a robot like this, it's game over. It can't continue. If some of these things are placed in different locations, something falls off here, it usually can't deal with it. So it's all about adaptation. As you know very well, a lot of the big challenges in robotics today are all about making adaptive systems. So back in around 98, I came to do my postdoc here in the US. I went to Brandeis University, and I met Jordan Pollack, and he told me, let's try to breed robots. Let's try to, instead of sitting down at a desk and designing robots and trying to get it right, and it turns out that it's a very difficult thing, let's just throw a bunch of robotic parts in a big simulation, let them connect to each other in lots and lots of random ways, evaluate how well they do. The better ones at some task get to reproduce. We'll copy them with small variations, throw them back in the simulation, and we'll see what happens. So we'll let this thing, and we'll learn to simulate a couple of basic building blocks: motors, wires, bars, actuators, and let's see if we can get a machine to crawl across the floor. So that was the first very simple idea, easier said than done. At the time, we had to code our own physics simulator. Now you get them, you see them everywhere. At the time, it was difficult. computing. This is 99, so it's not prehistoric, but even then, if you wanted to get any kind of computing power, you got to have a 16 processor silicon graphics machine, which is probably less powerful than your cell phone today, but at that time it was a big deal. We got one of those. We wrote our own gaming simulator, physics simulator. We threw in all the pieces and we watched what happened. So in the beginning, nothing happened. So these are generations. We have thousands of robots competing with each other. And this is the speed that these things are moving along. In the beginning, we're just getting lots and lots of pieces of junk. Piles of stuff all together, connected in weird ways, but not going anywhere. After a while, something interesting happened. After a couple of generations, maybe 100 generations into the process, suddenly a couple of wires connected in some way to a motor that made this pile of junk vibrate. And that vibrating pile of junk was able to move just a little bit. And it wasn't very much, but it was infinitely better than the other piles of junk that didn't move at all. And so it began to replicate. And suddenly all the pieces are vibrating and moving along, and gradually the process takes over. So every dot here is a robot, and that's the performance. You can see over time, suddenly there's these jumps and the machines begin to move faster and faster. Here are examples of two of these robots crawling across an infinite plane in simulation. And of course, to take it one step further, we actually 3D printed couple of these robots, and that was a relatively new technology at the time. And here are these two robots crawling across the floor of the lab. Now these are not very, these are fairly simple robots, but when you look at them, you have to remember that sort of they weren't designed explicitly by an engineer. We sort of set out a high-level task. We threw in a couple of components and we watched what happened. So that was sort of, kind of interesting type of thing here. And since then, we've been trying this in lots of other ways. This is a decade later, or more than a decade later. This is pretty recent. We tried to do the same thing with soft robots. As you know, soft robots are much more difficult than rigid robots to design, to simulate, and to build. So everything is more difficult about them, but they are much richer in their possible behavior. And just to give you an idea what that looks like, I'm playing back evolution of soft robots. You can see in the beginning they're kind of pretty lame, but gradually these robots are made out of 4 different materials: hard, soft, and 2 actuation materials actuating in opposite phases. And this is evolutionary time. This is generations. And gradually, it's learning how to move. It's kind of pretty cool to watch it and see how it does. And so we're getting a galloping. There you go. So that took like almost a decade to get to that point, not because the idea is new, but just to get the infrastructure for simulating soft machines fast enough to do evolution and being able to this is something we sent for review, so that's why. So back to our story. So this is one of these simple robots that we made back then. You can see it's sort of 3D printed. All the white stuff is 3D printed, but the wires and the batteries and everything else we had to manually put in. So at that point, we sort of split our research into 2 paths. One of them has to do with new manufacturing techniques, 3D printing, which is something I'm not going to talk about today. But the 3D printing focuses on how we can actually print also the motors, the actuators, the batteries, the wires, the whole thing. Because wouldn't it be great if we could print a complete robot that would actually walk out of the printer, batteries included? Because if we can do that, the design freedom to create that robot and to sort of breed these new shapes would be incredible. We'll really get new kinds of robots. But I'm not going to talk about that. Although we have been able to print some batteries and actuators and other things, we haven't quite gotten the robot to walk out of the printer. So I'll talk about that maybe next time I'm here. But meanwhile, let me talk a little bit about what happened next. This is a blurry picture from a TV where my advisor and I are showing one of these printed robots to Alan Alda, who was very unimpressed because it doesn't look like a particularly interesting, capable robot compared to what you can sort of see in movies and so forth. And here But it did make it to the front page of New York Times. Robots making robots. They told us they had nothing else to put on the front page that day, and so they put it there. But for me, it was a great time because I got my faculty position at Cornell based on that accomplishment. And I promised them that I'm going to move from just making these kinds of simple robots to making something more sophisticated. So they let me go. They went on a limb and tried to see if this kind of technique will actually produce something. But I knew that I'm not going to get tenure in a mechanical engineering department making plastic robots. I'm going to have to make titanium robots. And so we built our first, it's actually aluminum, it looks like titanium. It's a much more sophisticated robot. It has pneumatic actuators, it has a paintball canister in the center. It has 12 pneumatic valves here. They turn the air into these actuators. This thing contorts and can do lots of interesting things. And it's actually powerful enough that you can jump in the air and do loops and things like that. It's a very powerful machine. And what I thought is, okay, if I can just get this evolutionary stuff to run, I can get this machine to gallop through the fields. And surely I will get tenure for that, because nobody was able to do that. And the machine is powerful enough to do it. All I have to do is let it train. So we built this big cage. We put the robot in there. There's a camera that watches the robot. It actually watches this red dot here, and you can see how far the robot moves. It's breathing. We have lots of controllers, initially random, that turn the valves on and off at random times. The robot does its thing. It moves or doesn't move. And then the sort of evolutionary algorithm takes the better controllers, cross-breeds them in some way, tries them out again. Very simple algorithm. And we hope that by the end of the night, we'll have a robot galloping in the field. So we let it run here. It's a fairly automatic process, so the camera can do everything. The only thing is there's underneath here, there's a graduate student. And the graduate student, once in a while, comes out and pulls the robot out of the corner when it's stuck. But except from that, apart from that, it's a purely autonomous learning process. And you just leave it overnight, and you come back the next day and you see what happens. So we came back the next day, and what we got is this. So here's playing back some of the behaviors. In the beginning, sort of random kinds of behavior. You see, it's not going anywhere far, and gradually, it learned how to move. You can see here some of the behaviors, and it's gradually becoming better and better. But as you can see, I wasn't going to get tenure with this machine because it learned, but it didn't learn fast enough. So if you look at this for a moment, let's step back for a moment and look at these two projects. So first project, we used evolution in simulation, and it worked very well, but the robots that came out of it were very simple, and it only worked because the robots were simple. So the more complex the dynamics, the more difficult it is to do this sort of design automation in simulation and hope that it works in reality. There is a gap between simulation and reality. What works in simulation doesn't necessarily work in reality the more complex the dynamics are. So it doesn't scale in terms of complexity. Second project, we did everything on the real machine. There's no simulation. There's no gap. The problem is it takes too many physical trials. There's a limit how many trials you can do overnight. Learning. And I'm hoping that you'll see the connection here to this idea of a robotic scientist in a moment. So we start off with a simulator, and it's going to be a very bad simulator. This is why I put it in quotes. It's actually not an accurate simulator. It's a bad simulator. But it kind of works. We use it to breed robots, and then we take the best robots, we try them out in reality. We build our best robot. Now, because the simulation isn't very good, the robot that we build in reality isn't going to be very good either, but we're going to collect data. We're going to collect actuation and sensation data from that robot. Motor commands, let's say, an acceleration. And we're going to take all that data, and now, and here's the trick, we're going to breed or evolve simulators. So just like we evolve robots, we're now going to evolve simulator. What's a figure of merit of a simulator is how well it can retrospectively explain the relationship between actuation and sensation that the robot felt. In other words, how well it can simulate everything that is around. And so we take the best simulator that we have, we use it to evolve a new robot, we take the best robot, we build it, it still sucks, but we get more data, we improve the simulator and so on, and we go in a cycle like that until we get something that works. So essentially what we're having here is a sort of co-evolutionary process, somewhat like a predator-prey, two things co-evolving, where the fitness criteria or the optimization metric for each of them is a moving target defined by the other one. So it is sort of a very interesting dynamic, very difficult to sort of predict and analyze, but if this works, there's sort of an arms race. And the relationship between these is somewhat, it's not exactly predator-prey, they are sort of antagonistic, but they also help each other sort of move up. It's a little bit like professor-student relationship, right? It's sort of, there's some, you know, it could be an arms race, but it can also sort of move everybody forward. So let's see how that works. So this is the third robot. This is already my fourth year, right? So the pressure is on. And this is a four-legged machine, as you can see, and it has 8 actuators, 2 on each leg, 1 at the hip and 1 at the knee. And this machine needs to learn how to walk. It also has 2 sensors that tell it how it's tilted left and right, forward and backwards. So a very simple machine, looks complicated, but just 8 motors, 2 sensors. And but the trick is that this machine has no clue what it looks like. It doesn't know if it's a snake, a spider, a tree. It doesn't know how the 8 motors and pieces are connected. Okay, it just has these 8 degrees of freedom, and it has 2 sensors. But it needs to move as fast as possible. How does it work? So to understand what that means, imagine yourself for a moment sitting in a black box with no windows. All you have is a chair. You're sitting on that chair, and you have 8 knobs in front of you. And you turn these knobs, and you can feel the box tilting left and right, forward and backwards. And you need to move as fast as possible in some straight line. How do you do that? Now, that is maybe what a brain of a newborn child feels when it has actuators and sensors, so to speak, and it needs to do stuff, but it doesn't know how it's configured. So this is what this robot feels, so to speak, and this is the situation. So how can it learn? So that we're going to apply this idea of this hybrid simulation and testing in this way. The robot is initially going to make some random motion, randomly going to turn its motors in some way, and it's going to sense all the tilt angles, and it's going to create hypotheses about what it is. It's going to take, these are going to take form as sort of stick figures that try out different ways that the pieces might be connected. Now, you'll see this in the movie in a moment, and you will know that they're all wrong because you happen to know what the robot really looks like. But you have to remember that insofar as the robot knows, these are all valid hypotheses based on the brief interaction that it's had with the world. The next step in the green box, and this is the critical piece, it's going to do sort of active learning approach where it's going to look for what action to do next that causes all these models to disagree the most in their prediction, the most variance in the prediction. So it might be that activating one motor causes all these models to predict that it's going to tilt left, and so that's not a good experiment to do. But maybe activating 3 motors at a time in a particular way will cause some models to tilt left, to predict they're going to tilt left, and other models predict the sensation is going to be tilting right. So doing that experiment will eliminate half of the model. So it's looking for the most disagreement in sort of active learning process. So it looks for that action. It takes a lot of time. It's just sitting there thinking about it, and then it will do that action. Eliminate some of the models, improve others, again look for disagreement, and after doing this for a while, when these models cannot be made to disagree anymore, it will figure out a pattern of locomotion that will make the model move forward. And because the model is pretty close to reality, it will make the model move forward, will also make the robot itself move forward as well. So that's the basic idea. Obviously, devil is in the detail. How do you compare these noisy signals to know if they're actually different or not? There's a lot of sort of details to work out, but that's the basic idea. So here it is, one of our first runs. As you know, with robotics, you always have your camera rolling because it might be the last time the robot works. But here it is, unplugged itself and died. So we tamed it a little bit, tamed it down, make sure it doesn't explore too rapidly. And here it is, the robot is doing its first experiment. Here are all the hypotheses it's created of itself. They're all wrong, but they all cause the center block to tilt in the same way. So insofar as the robot knows, these are valid hypotheses. This is the 8th out of 16 brief experiments it's doing. And here are all the hypotheses it's created. It's beginning to figure out it has 4 legs, doesn't quite know where they are. And here's the 16th out of 16 trials, 16 experiments, and it pretty much figured out the 4 legs. Didn't quite get the positions right, but it's close enough. So this whole thing takes about 4 days to run. And here it is. It's actually, the robot moves slowly. It's my laptop that's making the video like that. We were hoping to get an evil spidery walk, but instead we got this lame way of moving forward. But when you look at this robot, you have to remember it did not have a model of itself to begin with, was not programmed explicitly to walk, nor did it do trials of walking before this. So we sort of managed to sort of bypass these challenges and get it to find a way back, so it's okay. And here you can see the robot's self-image also loses a leg. This takes about a day. The robot's self-image loses a leg. It doesn't quite lose it just makes it very small here, you can see. And it finds a different way to move without this leg. And I know it's very sad. We put it back, and the robot is happily retired now. So, but when you look at it, so you can probably manually program a better way to get this robot to move forward. But the point is that there wasn't a sensor that said leg came off, switch to plan B. Instead, the leg came off, dynamics changed, self-model changed, behavior changed. Right? So remember, we were after adaptation, and this is all about adaptation, about sort of self-modeling. So there's a lot of outtakes here. When I have this robot is trying to do other things and figuring out how to move. I just read a blog recently of somebody commenting about this robot, saying that they've never seen a machine that made it look like the machine is really trying. Like, you know, if your car breaks down, it doesn't really try to keep on keeping on, right? But this thing, there's something about this that looks like it's really trying. But anyway, so some statistics. These are 30 independent runs. The robot starts at the origin. The red dots is what a random controller will do to the robot. The black is where the robot thinks it's going to get to, and using its internal model that it develops, and the blue is where it actually gets to in reality. So just like anything else in academia, this robot has an inflated self-image. But that inflated self-image does allow it to make the right decisions, and that's an interesting thing. I gave a talk about this in a social science conference recently, and people were asking, is it better to have an inflated self-model or a deflated self-model? And there's an interesting, this is sort of a way to you know, another window to look at these kind of questions that are very difficult to analyze with people. So, you know, some of the things we're looking at now are robots not just modeling themselves, but robots modeling other robots by observation, trying to understand what the other robots can and can't do. And the really interesting thing is robots trying to model how other robots think. In other words, what is the controller of that other robot planning based on its behavior? And so that begins to touch on things like theory of mind and things of that sort. I think it's going to be very important when robots and humans, if you want them to interact on a daily basis, robots need to understand what the human is thinking based on what it's doing, and robots need to behave in a way that the human can understand what the robot is going to do. These are all very important social cues between humans that robots have not mastered yet, but are critical if we want to move forward. The really exciting thing for me is when we can get robots to model what they are thinking, which is very tricky because you sort of have to have two minds in a robot. where one mind in a robot can model what the other mind is planning to do. And this is touching a little bit on things like self-awareness and so forth, and thinking about thinking and all that. But I'm not going to talk about that. I want to show you what happened next in our story. So next thing that happened is that a student came in, another student, and said, this robot creates models of things by doing experiments. Let's connect it to an arbitrary experimental system and see what kind of model it creates. So arguably, if you have a general black box, something's going in there, there's some dynamics going on, things are happening, you can observe what's going in, you can observe what's coming out, and you want to create a model of what's inside the box. Now this thing might have memory, it might not be stationary, there's all kind of challenges in here, but arguably this is, you know, all machine learning or system identification, as it's called in mechanical engineering, or science, basically, as it's called in other places. And but what's interesting about this problem is that often you don't just observe inputs and outputs, but you can control the inputs to elucidate uncertainties about what's going on. So it's an active learning process where you can decide what knobs to turn to identify what's in the black box. So this is a very general problem. So we're going to take the same robot that I just showed you. This is the same slide. I replaced the robot with an arbitrary experimental system. Instead of models being made out of pieces of robots, we're going to make models out of pieces of some language that is relevant to whatever problem we're studying. Let's say mathematical language. So literally pieces of equations, plus, divide, multiply, open brackets, close brackets, things like that. And instead of thinking about actions that the robot will do to cause disagreement between models, we're going to create what kind of knobs to turn in the experiment to cause disagreement between predictions of these models. So same framework, just different languages around the circle. And we keep on doing that, finds how to cause disagreement, does the new experiment, gets more data, refutes some of the models, improve others, and so forth. And we can do that, we'll get models of some arbitrary system. Now, who's going to do the experiment? This is the algorithm does. Who's going to actually do the physical experiment? So it could be a disgruntled person who's going to actually be doing experiments for the robotic scientist, which is kind of interesting turn of events where the human is working for the robot. Or more, what is usually happening is that there's another robot that's doing the experiments. Or what is even more common is that you have, basically you do a lot of experiments in advance in a random fashion. You put them in a big database, and then when the robotic scientist needs a new experiment, it looks up in the database and uses and pulls out the experiment that is closest to what it wants. Now, it doesn't look at the rest, and this is really important. Only can see the experiment that it requested or the closest to it. All right, so we tried it out on a lot of different things. This is one of the first examples. This is a bridge I cross every morning when I go into Cornell. And you can see this is a footbridge and it wobbles, and when you cross it, you have a lot of time to think what would happen if this bridge wasn't as strong as it should be. This is, by the way, part of the Cornell defense system. In case you're thinking of anything, there's no way you can attack us. So when you cross this bridge, so we thought, okay, let's model this bridge, just put vibrators on different locations, vibrate the bridge subtly, sense vibrations in other locations, and from that actuation and sensation, we can create a model of the bridge and see which part is weak. And we did this. This is with the simulated bridge, not the real bridge. And we can find a weak element a lot faster and more accurately than conventional civil engineering approaches. So that just shows you this idea is not just for robots or for static for dynamic things. You can really do it with a lot of interesting ways. But I want to focus sort of the second half of this talk on this idea of using this to model to create mathematical analytical models. So to explain that, I need to focus for a second on this idea of symbolic regression. So I don't know how many people here heard of symbolic regression? One person, two people. Okay, two. So good. So I can explain this. So you all know what regression is, right? So you have regression, linear regression, nonlinear regression is when you have data and you have a mathematical model, and you fit the coefficients of the mathematical models to the data. And there's lots of techniques to do that, 51 different ways to do it in MATLAB. Everybody does it. Symbolic regression is when you don't even know what the model is. All right, so here's some data. Can anybody guess what is the mathematical function that fits this data?
X sin X.
That was very quick. Quick. I had a whole speech ready, but that was very quick. If you were trying to do that in your head, you were doing sort of symbolic regression. You didn't care about coefficients, but you took your basic functions that you are familiar with, trigonometric functions, linear exponents, and you try to figure out how to put them together to create something that qualitatively looks like the data. So we can do the same thing using these evolutionary techniques. So we're going to fit, we represent equations as parse trees. This is a tree that represents the equations x1 minus 3 times sine of x2 plus minus 7. We're going to crossbreed these trees and mutate them and do the same evolutionary stuff we did with the robots until they fit the data. So the fitness criteria would be to minimize, let's say, the RMS error. So in the beginning, we get random equations. They don't fit the data. Gradually over time, they get better and better until they fit the data. So that's symbolic regression. It's been proposed in the early 90s by John Koza of Stanford. There's only one problem. It doesn't work. Okay, now why doesn't it work? For two main reasons. One, it takes a lot of computational effort because you're testing a lot of equations against a lot of data. And the second reason is that it overfits the data. And this, and you can do all the validation and all that stuff, but it has the basic problem that many machine learning problems have. So what we did is a very small change. We now evolve models to fit the data, but we don't fit it to the entire data set, only to a handful of points. And what points are those? These points are also co-evolving to make the models disagree in their prediction to where there is the most error. So it's the same idea that we had before. We have two things co-evolving, an arms race. Models try to fit, reduce error on points, but the points are moving to where the models disagree in their prediction. So this thing sort of has two benefits. One is that evaluation is a lot faster because you're only evaluating in a few data points. You can upload a gigabyte of data, but it's only 8 points that you need to measure on. And the second thing is that it eliminates a lot of the overfitting. And give you an idea, here's a couple of runs that are on with the entire data set or with the co-evolved data set, and you can see it finds the correct solution faster and more accurately, and also finds solutions that are simpler. So for the same accuracy, solutions tend to be simpler and less overfit. And there's a lot more tests that I could go into, but to give you an idea of qualitatively why that co-evolutionary process is really, really important. All right, so what do we do with it? First thing we tried is to predict the stock market. And we spent quite a while doing this. I'm still here, so that didn't work, right? So it actually did work for other people later on, and I can tell you how. But it didn't work for us because it has to do a lot with what kind of data you put in, and there's other issues. We then said, okay, let's try to create find a formula for the prime numbers. Yeah, why not? So we put in prime numbers, we hit enter, we waited for a week, and we didn't get anything. We got some well-known approximations, but nothing groundbreaking. So, seeing that we're not going to be rich or famous, we decided to publish the paper. So we published the paper, and we immediately got an email from CERN, the particle accelerator people in Geneva, and they said, we have the perfect problem that you can look at. We have some gap in the atomic nuclei energy. I don't understand what the problem is, but they had 3,000 data points, and they said, maybe you can find the formula. We put it in, we hit enter, we wait, we get this beautiful formula. Explains the entire data set to 3 digits. We were very excited. We sent them an email, looked into flights to Stockholm, and we were very excited. But they immediately said, they wrote us back and they said, we already know about this formula. It's called the Weizsäcker's formula, and our formula is good to 4 digits. So they were disappointed, but we were actually happy because it means that we can find named formulas. And it means that if we just try hard enough, we can find something that is yet unnamed. But to kick it one notch higher, we said, let's look at dynamical systems. So instead, let's try to create differential equations. So instead of modeling equations directly fitting data, we take our time series data, compute derivatives, and fit the derivatives. And that's basically all it is. There's details in it, but this is how it works. So we tested it, and here are 7 equations from some glycolysis cycle in the cell, some complicated biology process I don't understand. It creates data. We simulated the equations. We got data. We added 10% noise, sprinkled 10% noise on it, fed it back in the system, and within about 4 hours it comes back and says, here are the equations that generated the data. If you think about it, it's pretty difficult to go from this to this, and it's not fitting coefficients. It's not just co-fitting, it's actually finding out the entire structure, and the only building blocks here are plus, minus, divide, multiply. That's it. So we armed with this tool, I started going on a crusade and saying, I have a hammer, give me nails. If you have data, I will model it for you. And we can write a paper together. It was very difficult, though, to get people to actually do it, to give us data. Because once you have the equations, you can do a lot of interesting things. You can understand relationships, a very sort of rich tool. And I'll tell you what happened in a moment, but we tried it in the lab also ourselves. And here's one of our demonstrations. This is a flapping, hovering robot that we built a couple of years ago. It's 3 grams. It's actually 299 grams for those of you who are working on this. And it's 3D printed, except for the motor and the battery. It hovers in place. It's stable, but it's very difficult to understand in terms of its aerodynamics. So we said, okay, let's see what happens. Let's take a video of this thing in slow motion, and we can measure the lift. We can measure parameters of how it flexes and all that. Let's feed it in and see what kind of equations we get. And then we can get an equation for aeroelastic lift in a flapping wing. People do spend careers on this thing, all right? So maybe we can do that. So I'm not going to show you the equation, but I'm going to show you how it compares to the rest of the literature. So I'm going to compare it on size, on complexity, and accuracy. Accuracy and complexity are the 2 main things in main dimensions of machine learning, arguably of all of science. We have models that are more complex but more accurate, and models that are less complex but also less accurate, and there's room for everything, right? So in between. And of course, if something is more complex and less accurate, it's usually ruled out. If something is more accurate and simpler, it usually dominates everything else, right? So this is sort of the landscape of scientific research. So here are sort of the different quadrants of more complex but accurate, less complex but less accurate, and here's the simple and accurate, and so forth. So where do the models that come out of this fall? So first of all, here are the models that people have published on aeroelastic lift on this particular problem. Some of them down the hall from my office, and each dot here is somebody's career, right? So it's especially the big dots, right? Then here are the models created by the software, okay? And what's interesting is that, first of all, here's what polynomial fits of various degrees. This is where they lie on this data. And you can see it sort of dominates this entire area. So it's simpler and more accurate. And it's also readable. So we actually look at the equations. We can see a lot of the conventional elements in there, plus a couple of new terms that are not existent. Here's another example. This is more of a Mickey example. Somebody came in and tried to model road-tire interaction. Very important things in automotive industry, in gaming industry, in racing, maybe autonomous vehicles. People spend a lot of time trying to create these models. He bought all the data that is available on this thing, created models, and again, the model that it came up with is simpler and more accurate than conventional models used in industry. Here's the conventional model, the Pajeca model, and this model is simpler. A little bit is an order of magnitude simpler and a bit more accurate. So this is just an example of applying this to lots of different things. And I've seen that usually when people run this, they get a whole series of models. And if there is a ground truth that's very interesting, suddenly there's a drop. You can get, you know, you can get improved error up to a point, and after that point, increasing complexity doesn't give you much improvement in the error. So there's this big cliff, and at the bottom of the cliff is the gold, is the equation that you want to look at. If there is nothing in it, if you're trying to model random data, there's usually no cliff. Okay, it's just sort of a gradual trade-off. So back to the story. I was giving a talk about this somewhere, begging for data. Eventually, one guy, Grohl Sewell, came to me and said, I have the perfect data for you. I have single-cell dynamics data that I record from individual cells. Most biologists at the time recorded data from vats of 1 billion cells, where all the dynamics was sort of washed out. But this guy records individual traces from individual cells. So he gave me 60 of these traces, 2 traces per cell, and said, create the model. Call me when you have something. So we put in this data. We hit enter, and we waited. We waited for a week, and we got these 2 models at the top. So I don't know if they're good or not. I sent Grohl the equations, and he sends me an email back and says, this is total crap. It's not even biological, and it is totally meaningless, and it doesn't work. So we were very depressed, actually, from this comment. And we were thinking, okay, we're doing something wrong. So first thing is that we're using the wrong alphabet. For one thing, one of the building blocks that we gave it was sine and cosine. Sine and cosine are irrelevant in biology. So that's our engineering heritage. So we took those out. But it was obvious that we are missing some building block that needs to be given to the system in order to model biology. What was that building block? We thought about it a lot, and we realized the missing building block was time delays. In biology, time delays are very important. In physics, there's no time delays. It's instant. In biology, there are diffusion. There's all kinds of things that don't happen exactly when they're supposed to. So we add in time delays, and bam, we get 2 equations that explain the entire data set. I send an email to Grohl, and he emails me back and says, we have a problem. Here's the state of the art. And your equations are simpler. And they're more accurate. In fact, these equations are symmetrical, and these aren't. So insofar as I know, these must be closer to the truth. But there's only one problem. We have no clue what they mean. And while here every letter is earned in blood, here we don't know what these coefficients are. And we try lots of correlations and generating data from this and mashing it up. And there's nothing simple. We spent a lot of time. I've circulated this equation to all the biologists I know and their friends. And nobody can explain it. But it fits the data. It fits new cell lines. It fits unseen data. It fits everything perfectly. So it's capturing something about it that we don't yet understand. So I want to end with this, talking a little bit about meaning, the search for meaning. I know it sounds very grand, but what I mean here is trying to understand what these equations means, because this is sort of where we're at. And the approach we took for this is basically this idea of searching for invariants, searching for things that don't change. So what do I mean by that? I want to step away from purely finding correlations. You know this story that if you mine data from a supermarket, it's really been done, you find that people that buy diapers on Thursdays nights also buy beer. That comes out. It's a real story. And if you run a supermarket, you don't care why. You just move the cart with the beer next to the diapers, and you sell more. And that's it. But if you're a scientist, you want to know why. And a lot of people, you're probably already trying to figure out why that is happening. So if you want to figure out why that is happening, the idea is to look for an invariant. So what's an invariant? An invariant is something that isn't changing. So I'll give you an example. Here's a pendulum. It swings back and forth, okay? And you measure 2 things in this pendulum: angle and angular velocity over time. Angle and angular velocity, you have traces of these 2 variables. Now you look at this, you stare at it, and you ask, what is not changing about these 2 variables? Is there some constant? No. Is the ratio constant? No. Angle and angular velocity. Can anybody say what's not changing about these two things? What combination of these two things isn't changing?
Period?
No? No, well, that's true, but that's not the only thing. Not a rhetoric question.
Also, it's potential and kinetic energy.
Yes, perfect. Right, so the energy. So the equation that captures the energy of the pendulum is constant. The kinetic energy and potential energy. So it's a longer equation. It's known as the Hamiltonian of this thing. And it's not changed. It's more or less constant. And if you know the Hamiltonian of this pendulum, you know everything there is to know about it. It's dynamic, it's period, it's the fact that it's chaotic in certain situations. Everything is in that thing. So finding the invariant is the key. So it's very simple. With evolutionary algorithms, all you have to do is change the fitness criteria to finding an invariant. So we said, okay, we made the change. We're looking for an equation that takes in all the data and is more or less invariant across the entire data set. We hit enter. We wait for a week. And finally, the answer comes back. The screen blinks. And the answer is 42. Now, it's true. This is a function that is invariant across the entire data set. It's true. The only problem is that it doesn't use the variables. But it is a function that's invariant. In fact, it gave us a lot of other constants to choose from. So somebody said, another student in the corner of the room saw this and said, it's not a problem. We just penalize it for not using the variables. So wants to use the variables. So we add the penalty, we run it again. It's a bit slower. We come back. Later, the screen blinks, the whole thing, and this is what we get. So it's okay. So then another student says, I have this package, this open source thing that eliminates, it does symbolic math and can eliminate these things, and it's going to be fine. He codes that in, it runs 100 times slower, and we come back in 100 weeks later, and we get this answer. This is a little bit more sophisticated. It's not exactly a constant, but it's as close to a constant as you want, and it's still useless. So it's like arguing with a teenager. Okay, we get what we asked for, but it's not what we wanted. So what do we do? So not knowing what to do, at loss, I give it as homework in my class, and we'll see what happens. And so one student, Michael Schmidt, comes back and says, oh, it's easy. All you have to do is compute the relative derivatives, dx, dy, dx. You have a candidate function. You can compute the f dx or the f dy symbolically. You take the ratio, you get dx, dy, and you compare these things, and the system cannot cheat. It has to give you the right invariant. So he codes that in, and he hands in the 3 homework problems for real. Here's the data. I made it easy because it was clean data, right? So the homework had clean data. Here it is, and he finds the invariants. Perfect. So let's see what happens. We ran it again, a couple of different systems. This is our first. It's also air track kind of physics 101 thing. We ran it. There's a sticker, a red sticker, and a webcam watching it. It's collecting the data. What is not changing about this? It comes back with this. This is later. It also comes back with a Lagrangian, which is it is changing, but that particular way of formulating the error metric also gives you Lagrangians. We run it again on a bubble gum on a shoestring, and here it is, the Hamiltonian Lagrangian of a pendulum. We ran it again. Okay, at this point I wanted to really try it out. These are 2 oscillators with 3 springs. What is not changing about the red and the green curve? This is not changing, and that is actually the Hamiltonian of a double oscillator. And now we're getting sort of to graduate level physics. This is a Steve Strogatz and his double pendulum. And you can see the double pendulum swinging around. What is not changing about this? Well, here's the data. Here's the angular velocity of the 2 arms. Okay, what is not changing about this? Well, a couple of things are not changing. Here's the Hamiltonian of a double pendulum. Also, the high energy parts of the swing, momentum is not changing, and F equal MA, and all kinds of other things in there, all sort of discovered from watching this and crunching on 32 cores for about 24 hours. So we find Hamiltonians of pendulums, equations of cells. We find out invariants in biological systems, but we can't publish it because we don't know what it means. And we've tried a lot. Okay, we got rejected a lot because it always comes back, if you don't know what it means, we ain't going to publish it. And this is sort of, I think, a recurring problem. You know, at this point we said, okay, let's you know, publish the whole thing and see what people do with it. And we published it, and we started getting emails, and lots of emails, and all the emails said exactly the same thing. They said, I have data, I need to graduate, please find something in my data. and we became the bottleneck of graduation of a lot of people. And at that point we decided, okay, we're going to, you know, release the software. It's called Eureka with a Q, so it's misspelled, so you can find it with Google. It looks like a spreadsheet. You paste your data, you name the columns with variables, and you put in queries. You want Z as function of X and Y, you want an invariant, you want a differential equation. You say what the query is, and it finds F. It fills in the blank for you. It finds what F is, given building blocks that you need. So it's sort of cool. It comes back with a handful of equations on this Pareto front. Some simple, some more complicated. Usually the truth is somewhere in there. You get to choose which equation to choose, so you feel you're part of the discovery, right? But it's really part. It's in here. You got also to explain. Again, the true equation though tends to be sort of at the middle, and when you get this sort of thing, you know that there's nothing in your data. But increasingly, people don't even want to put in a query. All people want is this. So now we added that. There's a button there you can press, and it will text you when it finds the equation. So you don't even need to think about that. So a lot of people are using it. There's a couple hundred papers already with the main result produced by it. But most of the use is about 35,000 people using it, mostly for business, running small business, creating models of things that are not necessarily publishable, improving radon detection, estimating strength of wells. I mean, you name it, there's lots and lots of things. Somebody takes a big equation, creates data, and refits it with Eureka to find a simpler equation that's approximate but runs faster. Somebody else improves the detection in particle accelerator fivefold by modeling the nonlinearities. You can use it for classification, not just for regression, for modeling stochastic systems, which is sort of what we're doing now. So in the lab, we're focusing now on creating models of stochastic systems by essentially integrating stochastic building blocks as part of the model. So we can model distributions, creating models that are finite state machines, stochastic finite state machines, so we can track these kinds of signals. Even more recently, it just came out about a month ago, is that we can look at sparse samples of concentration of a population, very few samples, and detect the underlying reactions that led to these things. So for example, if you have, this is a Lotka-Volterra system where you have foxes and rabbits, foxes eating rabbits, rabbits reproducing, and there's some interactions. When there's a rabbit, there's two rabbits soon after. When the rabbit and the fox meet, there's two foxes later and no rabbits. and foxes sometimes die. So this is the law of the jungle, but we can infer that automatically just by tracking once in a while, once a year, the number of foxes and rabbits in the forest. And this is really powerful for sort of modeling chemical phenomena and things like that. So these sort of tools, and more recently we've been looking at sort of, we're scanning the web for data. Anybody that left a spreadsheet on the web by chance, we will find it and we will model it. And we will let them know if there's another data set that somewhere else on the web that is similar, that might have different numbers, but the underlying math is similar. So it's like a social networking for people with data. Tells you who you should be talking to. So Right, so to sum things up, I've showed you how evolution, we know it can't make Shakespeare, but it's interesting to see that evolution can find Hamiltonians and other things. The New York Times said theoretical physicists are not yet obsolete, but scientists have taken steps towards replacing themselves. I was very careful to show you that's not true, because scientists are needed to collect the data. More importantly, to choose what building blocks to use, because when we choose the wrong building blocks, we got total garbage, and to find and assign meaning to the result. Thank you.
We can take some questions.
Couldn't you, in a very similar fashion, learn the set of building blocks?
Funny that you should ask. So here's the case, for example, if you don't give it sine and cosine on the pendulum, if you don't give it cosine, it will make a cosine out of the sine. If you don't give it cosine and sine, it will discover a Taylor series expansion. But you can then do statistical analysis on this, find things that begin to reappear, and you can give those names, and you can call it new building blocks. So you can do that, and I think that's actually key to scaling. But there's a limit to how much that works. So can you go from deterministic to stochastic? You sort of need to discover random number generators, so forth. So I think that's the deep research question that's next, and it's not clear how to solve it.
Very nice stuff.
Thank you.
In the early thing with the dynamics of the system, I was wondering in what space are you looking? The rest of your talks are discussed that. But also I noticed that you're either in a flat environment or a uniform one, which simplifies the way the
Right.
sensing environment.
So you're talking about the robot or the pendulum?
The part about the environment was the robot and the thing that the helicopter.
Okay.
But what did you do for the space in which you look for models of the dynamics?
Okay, so in the cases where we created dynamical models for the flapping wing thing, for example, the basic building blocks were algebraic operators, sine and cosine. That's it. So it's not completely unbiased, but it's pretty open. But the first robot that I showed you was very constrained. So there we said there's 8 pieces, they're all rigid, and you have to figure out what's the topology of 8 pieces and where along the robot, where along each other they're connected. So there's a little bit of metrics and topology.
And what about dynamics?
Oh, the dynamics in the robot, they were built in. So there's a physics simulator. So only that simulated the dynamics. It only tried to figure out what is the topology of the robot, just the self-image. In the second, in the pendulum, it rediscovered all of the physics. Yeah.
So I didn't quite get how does it help to fit on the smart points to avoid overfitting? Because the usual approach is just penalize for complex models by some number of coefficients or terms, but your approach is just fit a smart point.
Right.
Why did you choose that?
Right. So I have to. So the question is, how do we avoid overfitting? So this is. So I don't know why exactly it works. So this is only empirical. We didn't study it very deeply. First of all, there's no penalty for complexity. This is a very important thing. There's no penalty. But I think what is happening is when you have this co-evolving data set, when models overfit, they disagree. There's many more ways to overfit, and they tend to disagree on how to overfit, and then the data, because it looks for disagreement, moves to the place where there is overfitting and sort of disbands the bad models. This is sort of a hand-wavy experiment, but empirically, we tested this on thousands of equations. We actually generated random equations, generated data, ran it, and we saw systematically the kind of active learning. It doesn't completely not overfit, but overfits a lot less.
But then later on, you have actually somehow measuring the complexity of the
Right.
equations,
That right.
you are plotting those solutions.
Right. That's just for display, and in this case, we're just counting the number of nodes in the tree. But that's just for display.
What if you're like collecting wrong data, like that double pendulum
I mean, the sensible thing would be to collect the two angles of the two pendulums. What happens if you're naive and you just say, just track the endpoint?
Right. Then two things might happen. Or one is that you get a more complex model that somehow backs out the angles from the endpoints if you're lucky. And if you're not lucky, it's not going to find anything. In which case, you're going to have the Pareto front of complexity versus accuracy is going to look sort of like a basic trade-off, which means it can't find anything. And actually, when that happens, the AIC predictor, according to the AIC metric that comes on top, is that the only thing you can predict is the average. So it's pretty nice to see that when you give it something that's too complicated, it just gives you the average. Yeah.
You said that it works very good in very different areas. Why it didn't work in stock market?
Well, okay. So because if you just try to fit a curve to the stock market, it's not going to work. Well, first of all, it does work. I've seen a couple of blogs of people using this to predict the stock market, and then the blogs were taken down, which means that it's working. So I think it is, but it has to do with what data you feed in. And also, I think it has to be stochastic models. And if you try to fit sort of deterministic models to something that's inherently stochastic, like you're trying to fit, you're flipping coin and trying to fit a curve to it, you can only predict the average. You just need a different language, so it has to be stochastic. So I think that's, but the people who are using it for the stock market, I believe, are using different data, and they're trying to not to predict what the stock value is going to be tomorrow, but they're trying to predict which stock to buy, or they're trying to predict volatility, or they're trying to predict margins. They're trying to predict something else. And what to predict, basically what question to ask, that's the key. And that's the part I don't know.
Is selecting the building blocks the same as like automatic generation of features in other machine learning?
Automatic generation of what?
Of features.
Of features. In a way, I think the building blocks, I would, to the extent that plus, minus, divide, and multiply are features, then yes. But you could have more sophisticated building blocks. For example, sine and cosine, are they a feature of this? I don't know. It's more like a language. I don't think it's exactly a feature. It's more like selecting a language, but there's probably some relationship there. It's a good question.
So depending on who you're talking to, you might lose credibility if you mention that you're using evolutionary methods.
Right.
Has that been a problem for you? Have you been tempted to maybe use the same kind of thing with different names?
Now asking this is a tenure level question. Yes. So evolution is controversial, especially in computer science. But I think it's gaining acceptance. And yes, in the beginning I had to be careful. But now I can speak freely about it. And I really do think that in case you know what this question is about, for evolution has been around, evolution computation, for maybe 30 years. Personally, I think that sort of the newer age one that has to do with coevolution and estimation of distribution, some of the sort of newer things really make it very, very powerful to the point where there's no argument that it's a useful and viable tool. But it is still an art.
I noticed that none of the problems that you touched on involved policy learning or decision-making learning. Is there an inherent shortcoming that is?
No, it's just we've done quite a bit of that, where we actually learn controllers. We evolve controllers to control. Actually, I have tons of robots learning to walk or move, things like that, where the controller has been evolved. I just didn't show it. And other people are using it as well. But I am not familiar too much with using sort of this coevolutionary thing for policy design. But I think it's a good idea.
Maybe one more. I noticed that the effort in one of the graphs, the effort was measured in number of points evaluated, but there's effort involved in finding the points to be evaluated. And how does
Right.
that compare to going through the data? And
Right. So the effort to find the points is also measured in number of points evaluated. Because when you look for points, you're looking for the points that cause disagreement. So you have to take points, run them through all the functions and evaluate them and see if they cause disagreement. So it's still, so I think number of evaluations is a fair metric. You know, you could measure, it correlates to CPU, but the nice thing about this is that as CPU gets faster, we can still compare to our old results because we only count point evaluations. So it's a sort of practical thing.
Sorry. How high dimensional functions have you learned? So how many input variables?
This is an excellent question. So I should say it scales. So I've seen people work with about 1,000 variables, but not that all of 1,000 variables are in the equation. They have 1,000 variables and the equation might use 6 of them, but it has to figure out which 6 out of 1,000. So I think it scales pretty well with the number of variables in the data, but not very well with the number of variables in the final equation. So if the final equation is looking for is very complex, it involves many variables, that's bad. But if you have a lot of variables and only a few of them are used, that's it scales better. I hope you see the difference. But
You should probably, maybe one more question.
Okay.
2 questions.
For whenever you were learning configuration of the robot, how did you solve the imaging itself? So in certain configurations, motor positions.
oh yeah, so well, how do we stop the robot from damaging itself when it's trying to learn? That's a good question. In the first time we didn't, and it damaged itself. Second time we just restricted it from going too far. But in practice, that's an excellent issue because there's a risk to learning, and capturing the risk versus glory in every learning action is very tricky, and you don't want to walk off a cliff to learn what it feels like, right? So that's a really good question. We haven't dealt with that. I think it's a very interesting direction.
Question over here.
So you might have a system which is sort of, if you try to find one equation that describes the system, that could be really complicated, but it might be governed by very simple equations in different regimes. Is that easy to learn in your framework, like a case-by-case?
Yeah, so I haven't shown anything about that, but we have a couple papers on hybrid systems, where you can say this is a very complex dynamics, but it's actually 3 simpler dynamics and the switching between them. So we've done some work on that putting this technique inside estimation maximization loop, which tries to figure out what are the transition rules and partition the data and model each part separately. We've also done piecewise modeling, where you try to model the left half of the data and the right half of the data, or something like that. So there's a lot of things that you can do that way. Absolutely.
And it can learn where it's split as well.
Yeah, so it has to learn where to split, exactly.
Okay, last question back here, and then if you'll,
One fundamental problem in multivariable regression is that you have redundancies in input variables, and how does that work? If you try something like you have 2 measurements which are actually measuring the same thing, what happens to your algorithm?
That's a good question. I haven't explicitly tried it, although I believe it's probably happened many times with real data. That's a good question. I can't, I mean, from the simplicity point of view, it's probably going to choose one or the other, not choose both, because that makes it more complicated, unless there's noise. So that's interesting. It probably depends on things like the level of noise and if it can gain more reliable information by using multiple sources. That's a really interesting question.
okay, I think we'll conclude here. Let people go that want to go, and then if you have 3 minutes, you can probably answer further questions. But I'd like to thank you.
Thank you.